Okay. So that looks like it has started. All right. Thanks everyone for joining for our seventh targeted technical advisory group meeting. Just a reminder that these meetings, we're heavily focused on the methodology around distribution system planning, specifically for this meeting. We would like to hear your feedback on your thoughts on how we are approaching distribution system planning, and feel free to interrupt at any moment throughout the presentation. Feel free to post questions in the chat. You can also just raise your hand, or you can just jump in off of mute and interrupt us. If you do jump on, please make sure to introduce yourself and the company you're representing. That way we know who's speaking. When I pass the meeting over to Kathleen, I'll put our IRP webpage link into the chat again. That way everybody has access to the website. You can check it out for all the previous targeted tag meetings. We have the video recordings posted for all 6. I think we're still finalizing the minutes for targeted tag 6, but those will be posted soon. Okay, so I should have introduced myself. Brian Robertson, manager of supply resource planning with Cascade. Just a reminder on, I did the reminder on the introductions. Please introduce yourself if you come off mute. I'll go through a safety moment real quick, and then I'm going to pass it over to Kathleen, and she'll be doing a presentation on our distribution system planning. And then we'll open it up at the end for feedback. If you want to save your feedback for the end, that's more than welcome as well. And then we'll discuss next steps. Okay. So yeah, so the quick safety moment. I'm sorry, I should turn my camera on. There we go. So I know it's getting warmer out there. It's been in the 80s here recently. It is going to cool off a little bit, which is nice, but make sure when we're in the summer and it's 90, 100 degrees out that you're staying hydrated. Drink plenty of fluids, at least 15 ounces before starting, especially if you're working outside or playing outside or going to a barbecue or something. Try to avoid dehydrating liquids if you're going to be outside all day, such as alcohol, coffee, tea, caffeinated beverages. Make sure you wear protective clothing that is lightweight, light colored, and loose fitting to help protect against the heat. Make sure you pace yourself. Don't go too hard if you're working or playing outside. Make sure you pace yourself, take breaks if you need to. Work at a slower pace if it's really hot. Schedule frequent breaks. Make sure you take breaks, get a drink, stay hydrated. Make sure you wear sunscreen and a hat to avoid getting sunburnt. And then make sure you stay aware of any signs of heat-related illness. Know what to look for. There's more over here on the left side, the more you know. So there's some information on heat stroke, heat exhaustion, heat cramps. Make sure you look out for this, not only for yourself, but other people. If you see someone struggling with cramps or acting dizzy when they're out in the heat, please check in on them. Make sure to avoid direct sun and then eat smaller meals if possible. Okay. So that's it for the safety moment. I'll pass over the screen sharing to Kathleen.
Sounds good. Let me get my screen set up.
Okay.
Okay.
Perfect.
Okay. Well, hi everyone. I'm Kathleen Campbell. I'm a senior engineer in our engineering service group. Today I'll be presenting on distribution system planning. So just as we do these, I think everyone's aware, but feel free to interrupt. I only have 2 screens, so I can't see the team. So let me know if there's comments, or just feel free to just just interrupt. I think that's welcome. It's probably my preference, and then we can just get things addressed. But we'll work through the slides together, and then we can answer questions as we go, and then we'll have a chance at the end to ask more questions or get some more feedback from the group. All right. So today, this presentation will cover, this presentation is going to really build us up to our July tag. In our July tag, we're going to cover our projects and go through alternative analysis. So this project will get us like up to speed on what we're doing up to that process. So it'll prepare us to go over the actual projects and have good discussions on those. Today we're going to cover our distribution system modeling process, how we identify our system deficits and constraints. Once we have those system deficits and constraints, how we work through solutions to address them. And then once we have those solutions, we normally kind of do something called alternative analysis, where we lay out multiple alternatives, and then we review those and how we select the project and then get it into the capital budget. So we'll set us up really nice for July, where we'll be kind of going through those projects and sharing the alternatives considered for the deficits that need to be addressed. So we'll start with distribution system modeling. Just before I start, I want to get everyone up kind of familiarized on our system dynamics. So Cascade Gas operates a diverse range of piping, diverse diameters, diverse materials, diverse operating pressures, kind of as you can see on the screen. And this also states our miles in Washington of distribution and transmission, and Oregon. So just lots of diverse pipelines and system dynamics in our system. In addition to pipe, we also operate a diverse range of facilities. So those facilities include regulator stations, valves, and equipment such as odorizers, heaters, and compressors. So here's some photos of some of the facilities, things we're doing maintenance on, also looking at sizing on, making sure they're meeting all of our needs. And then to get us a little further into understanding our system, I'm going to go through, this is a high-level example of kind of our systems and our dynamics. So this is very high level. In green, that is the interstate pipelines where Cascade Gas receives our gas from. Typically for Cascade, that's TransCanada or Williams Northwest Pipeline. From those, we have gate stations. They're basically taps off the pipelines, off the interstate pipelines. Those gate stations, Cascade Gas, we take over pressure regulation and will odorize the gas. And those systems kind of feed our distribution system. So it's the start of our system. In red, those would typically be like our high pressure lines. So outside of, downstream of gates, we typically have high pressure lines. And those high pressure lines will feed our regulator stations, which feed distribution systems, which are in blue. That kind of feeds our residential commercial loads. And then also we can have some industrials, and those can be either off high pressure systems or off the distribution system. So that's just a high level look at what we're looking at, from our tap, all the way down to that, the service on your house. To model all that, and all of our modeling, or the main tool we use for our distribution system is Synergy Gas. This model is supported by DNV. Our Synergy Gas models incorporate our total customer loads and all of our piping and system configurations, which would include like regulator set points, size of those facilities, things like that. Synergy Gas is an industry-used hydraulic modeling software that predicts flows and pressures on systems based on gas demands. And typically we use them for peak weather events, but you can actually use Synergy to model any weather event. And we'll go over some of that. And then for Cascade Gas, our models, they're really important. So we rebuild them and validate them every 3 years. And then we maintain the models between rebuilds. So a great tool and resource, that we put a lot into to keep accurate. And actually right now we just completed Cascade's 2023 model updates. So for this IRP, we will be using Cascade's new models that are just getting rebuilt. I guess they got rebuilt and validated, and they're getting used by engineering, or we're just getting them kind of set up. And that'll be what we do our 5-year growth modeling with. So kind of exciting news that we got the models in time to do for this IRP. Oh, my computer might have skipped a slide. Okay, let's check. There we go. There we go. So then I just wanted to kind of let you, so you get an idea kind of what Synergy is. This is just an example. So this is a screenshot from our GIS. This is actually the Kennewick district. You can see there's some red dots on there. Those are reg stations. And then I can see some, I think green is steel and then blue is plastic. So you can see some pipe. I know there's typically high pressures are where the reg stations are. And then distributions, typically that plastic pipe operating at 60. So this is just an example, but basically all this information goes into Synergy for us. And then this is that in Synergy. So you can see like the reg stations, the piping all the same. It feeds from GIS. So it's really accurate, up to date on everything that's been added to our system. And then one note I'll just make is each of our systems are unique. They can be unique in the customers that are served and the pipeline characteristics.
Hey, Kathleen, just jumping in, let you know, 3 hands have been raised. So I just wanted to
Thanks,
catch you before we moved on.
Oh, okay. Let's pause.
Go ahead, Byron.
Hey, Byron. I can't hear you. Is it me or did we lose something?
Can't hear Byron either.
Okay. I thought I maybe lost my connection. I was about to freak out.
Can you guys hear me now? Did that work?
Oh,
yes.
Yeah,
yes,
we can hear you now.
Okay, sometimes you just got to turn things off and turn back on again. Okay,
Yeah.
So Byron Harmon here from Washington UTC. I want to start by apologizing that staff didn't get its pre-tag feedback back to you guys in a timely manner. But could you go back to slide 7, please?
Okay, sure. Yeah.
So in previous staff comments, we had raised some concerns around like hydrogen embrittlement with steel piping. I don't know what the literature says around polyethylene and hydrogen embrittlement. Is that a thing? Have you guys investigated hydrogen embrittlement with polyethylene pipes?
I can touch on this a bit. I know the hydrogen's kind of new. We haven't had a project where we've done like a thorough evaluation of our system. I think you would just evaluate like the system the hydrogen's going in. Because like I said, we're diverse. So like as Cascade grew in our history, you know, towns were put in different eras or they grew at different times. So you could have different vintages of pipe out there, depending on, you know, the different dynamics going on as the system grew. But I know we've worked with GTI. We've been included in some of the hydrogen stuff. So as an industry, I know I've been involved in like several, like, I guess I know we've been in like conferences and AGA stuff and GTI, you know, meetings, I guess, or things like that. So I'm not sure on the industry answer on steel, but it would depend. I guess my answer would be, it would depend on your system you're putting it into and probably like vintages.
Yeah, I mean, my question is about the polyethylene pipe. Whether there's any...
Yeah, the same. Well, the poly changed over time too. For instance, like some utilities have the Adelaide, but Cascade does not. So an operator may have a different answer on that, but PE, I've generally heard it hasn't been an issue. I know I was part of an AGA thing where there's an operator in Hawaii that's been running hydrogen for years. And they use a lot of the same components we do, and they don't have problems. I think it's Hawaii gas. Yeah.
A question about the operating pressure. Have you guys done any assessment about how much you'd have to increase the line pressure in order to maintain the same like end use quality of the product if it's hydrogen blended fuel?
So we've done some like high level calcs. I know I've attended or I did like a hydrogen course through GTI. I think it was like a 1 day like engineering course on it.
Mhm.
And because I don't know if this is getting kind of technical, because the BTU's lower, you have to use more fuel. So you
Mhm.
either need a bigger line or you're right, you would increase your pressure. It would depend on your system dynamics again on whether you even could increase pressure. Because you either need to do a repressure test. There'd be things you have to do to uprate, and some systems might not be favorable. So, like I said, I think each system would get evaluated separately for that.
Okay. Have you guys started any kind of like like scenario planning around like what those kind of like collateral costs would be around hydrogen if it were introduced onto the system?
I think we've held off kind of till we have a project, as far as I know. And we might have some industrial service folks. I haven't heard of like a hydrogen hub, because what I understand is that hydrogen will be like in a hub. Like there'll be some area where like multiple businesses commit to hydrogen,
Mhm.
and then that system would be like its own separate system. So I haven't heard, or we haven't heard of those opportunities or interests yet in our territory, as far as I know.
Interesting. So
So
to make
others
sure
can speak up, but yeah, I think that's generally the discussions I've been in.
I'm understanding you here, it sounds like you guys are looking at hydrogen as being a parallel system as opposed to in like having hydrogen blended fuels on the system. Is that accurate?
No, I think you'd assess the system. I think you could put hydrogen into our existing system. So one example I've heard of that or the example was thrown around, and maybe there's business interest, but I know it was like our Boardman area, like the Boardman lateral. Because
Mhm.
there's a lot of like large volume agricultural customers, like a Lamb Weston, things like that out there.
Okay, I appreciate your clarification on that. Thank you.
Yeah, I think you'd look at the system, and if it has to be separate, or if your system couldn't support it, you might install infrastructure if your system couldn't support it. But I think you would need to do that, like that due diligence on your system
Thank
before
you.
you
Yeah,
put more infrastructure in. But yeah, anyone else can chime in. I talked a lot on hydrogen, which we haven't
yeah,
had before. So
this is Brian, and yeah, we're definitely looking at hydrogen as one option as a blend, and then the other option as a dedicated hydrogen pipeline to, let's say, like a large volume customer. So we're definitely weighing both options.
Will that be reflected in your like portfolio analysis and like scenario analysis in the IRP document?
Yeah, I would assume so. That's the goal.
Okay,
And
cool.
we may end up, I mean, if we find it not feasible to blend it, we may just pull that out. So it kind of depends. We're still doing research on it and figuring out which direction to move forward with.
Yeah. Thank you, Brian.
so do we have another hand that'd like to?
I know
Hi,
it
this is
will, and oh, go ahead.
thanks, Brian. Hi, Kathleen. This is Will from NWEC, Will Gerke. Does Cascade have any air steel or coal tar wrapped pipe on a system still in Oregon and Washington?
No bare steel. Happy to report.
Any like pre-Cascade natural gas pipe on the system, or it's all replaced at this point?
It hasn't all been replaced. So we still have some pre-CNG that is coal tar wrapped. We have replacement projects going on. I think we mentioned this a while back. I used to do pipe replacements. I know we've been doing pipe replacement back since 2012, I think. I started in 2011, so we increased them. So that's kind of how I got hired on, was increase staff to support pipe replacements. But yeah, our system integrity still working on. I know they did Baker City last year. I don't know what town they're doing this year.
So it's mostly in Oregon. Washington's mostly complete, you're saying?
No, I think they're doing Longview or Aberdeen, so I believe it's still ongoing. So they usually do a town in each state.
Yeah, that phased approach makes sense. Okay,
Mhm.
thank you.
Yeah. And number 3.
That was Quinn. Did you have the same question as Byron?
I did.
Okay.
Okay. Perfect. So it sounds like you guys are kind of thinking a hydrogen section in the write-up, just because we're having open discussion, like kind of our stance on it or something like that.
Are you asking UTC
Just Byron,
staff or
yeah,
Brian?
yeah. Would you recommend, or I know this is a lot of like collaborative effort, what you guys are looking for, so we can provide that.
So I guess the first thing is I don't think that our comments here should be in any way interpreted as any way trying to dissuade you guys investigating alternative fuels like hydrogen.
Okay.
So I just want to make sure that that's not like a subtext or something like that. We have to kind of, we kind of have to investigate all the different solutions out there, even if they do kind of raise these kind of problems. I think based on staff's comments from the last IRP, I think it would be useful to have a kind of like larger discussion around the kind of like difficulties in terms of like IRP planning around hydrogen. So like what barriers there are, what kind of questions still need to be answered before it can be implemented and stuff like that. And then from kind of like a hedging or risk standpoint, if we don't necessarily know when these questions will be answered, and so like if we start plugging hydrogen into our the optimizations, there might be a point at which we get to the point at which the optimization software says we should be taking on as the lowest cost resource, and then it's not available either because the infrastructure isn't out there and it's not available in sufficient quantities, or there's these kind of engineering impediments, or there's these kind of like collateral costs associated with it. And so it might be prudent to kind of have a kind of like hedging understanding about like what happens if it's not available in the future, but we've planned to put it on the system, sort of a question, if that makes sense.
Yeah, no, super helpful. So yeah, I took some good notes.
Thank you.
Okay, so anyone else or anything else pop up in those discussions someone wants to add to? I'm gonna try and figure out what slide we're on. Keep going. I think we had just done I think we're on this one. Yeah, I think we're wrapped up though. So now we're going to kind of get into our model building process and go over a little more detail on that. So when we rebuild our models, we take our current GIS data to do the spatial rebuild. We also export out our current CCMB billing data, and that data goes into a module called CMM, which is Customer Management Module, which is kind of a synergy interface. And that takes our CCMB data. The program takes our CCMB data to make an updated demands file. And I'll touch on that a bit in the next slide too, but basically it's like, so when we take the CCMB data, we take 5-year billing data. And in that 5-year billing data is up-to-date usage on the customer. So if, the customer changed or their habits changed or their equipment changed, things like that. Maybe they did some energy efficiency programs, things like that. So it's up-to-date billing, which is good. We want the best representation of loading on our models. And then once we get that kind of built and those processes done, we go through and we validate and calibrate. Validate and calibrate is kind of the same thing, but we validate each model and we'll do it to a recent low weather event. And we basically see how well our model that we built is performing to our existing data. So we'll check things like electronic pressure charts, which are ERXs, We use our SCADA data, which is data that comes into gas control that we have live monitoring on. Our Metrotech data, that's mainly used for our large volume customers. And then we can also go look at large volume usage. So we have lots of database on pressures and flows, and we can compare those in the model. Typically, a best practice for model rebuilding is for models to be within around 10% of the actual data. So that's the goals and typically what we get our models to perform to. And then once we have those validated models, we then will ramp them up to our predicted peak day models or design day models. Kind of use that term interchangeably. And that's kind of that cold weather event where we'd see peak demand. And we're going to cover that through a couple more slides. So data gathering, I just thought I'd show some screenshots so it maybe better understand it a little bit, just some visuals, good to see. So this is just our CCMB data. So this would be like an example of a customer and their monthly usage. All that goes into Synergy. Other data gathering, this is just a screenshot of our SCADA data. So this is our real-time and historical flow data and pressure data that comes into gas control that we can see semi-live. Gas control can see it live, but we can trend, pull this data for dates and times we're interested in looking at. Other data gathering, so I kind of touched on this, but this has to do with our peak day model. So these are our Cascades districts. So our models are all kind of built by district. And then each of our districts have, like I mentioned, we operate in a unique service territory. So there's different temperature on either side of the Cascades. And then even down in Bend, in Central Oregon, it's a little different too. So you can see in the range of average daily temperatures, there's some variability, throughout our territory. Generally, our districts that are kind of near the ocean are a little warmer. They're, kind of more shielded from the cold weather. But so we use all that. So these are our current heating degree days that we use. Based on average daily temperature. And the average daily temperature, I'll just cover that. It's the average of the day. So you basically take the high temperature and the low temperature and take the average. And then those build into a degree day. So for us, we call them peak, but you can actually have a degree day for any weather event. Like you could calculate your degree day for any day, today, whenever. And basically, the relationship correlates to 60 degrees. And the reason it's 60 degrees is Cascade uses that because that's when we've seen our customers turn heat on. I know this has come up, and so I'll avoid questions, but even in our areas other than Cascade, we do use 65, but Cascade has always held the 60 line. So either works because you can they correlate, so whichever one you use. So we do 60 because that's typically when people turn their heat on. So when it's temperatures below 60, it's chilly. People typically turn space heat on to warm their houses. And then when it's above 60, typically people are not heating their homes. So we use that. So you can always calculate, but we just take 60 from the average daily temperature. So for instance, if my average daily temperature was 10, I'd go 60 minus 10, I'd have a degree day of 50. So that's kind of how it works, or how we talk the lingo, and this is pretty industry standard on the degree day definition. And then with that, just touch on customer management module, CMM. So like we said, we get our CCMB data, comes into CMM. It brings all our data in and basically makes the demands files. And those demand files apply the load spatially in the model. So in our Synergy models, some of it has to do with file size. We don't model each service line. We typically put like service lines spatially into the pipe loads. And there's just things that less data points. So when it goes to run, it's a little more efficient, like from a data management perspective, and it makes the program run faster. So that's what CMM does. We just put all of our meter demands into the pipes. And that's basically what CMM does for us. There we go. So now we're going to talk how we get from a verified model up to a peak day model. So you can see in this typically this load temperature relationship will come from CMM for us. And basically as your degree day increases, which means it's getting colder, you typically need more heat. Customers typically use more heat, more space and water heat. So as we get colder, more heat. And this is basically a linear relationship. So CMM also will get us this trend line in the equation. It's kind of a best fit, but it's basically a linear regression. So you can correlate degree day to usage. And then I got a couple of examples on this one. So this one, for instance, this is a calibrated degree day. So this might be that cold weather event you calibrated the models to. So in this instance, the degree day is 40. So that would be an average daily temperature of 20 degrees. So 60 minus 20 is 40. And then if that's all the data you have, you'd still need to, extrapolate the loads out to get to your peak day, or, that day. And typically we get our degree days, which was that chart a couple back where we talked about the equation or the relationship between average daily temperature and degree day. We get those from regulatory for Cascade for our districts. So calibrate it, and then typically we'll ramp up to our degree day. So in this instance, if it was 58, we would ramp up. This line would kind of extend, and this would kind of be the load in our degree design day model or peak degree day. So 58 in this example, it's about 2 average daily temperature. So 60 minus 2 is 58. And then waste synergy, like I said, we put a lot of effort and time.
Kathleen,
Yeah, there's
we
usually
have a-
questions on that one. So yeah, let's
Yeah, we have a
see if we got
question
any.
from Byron.
Okay.
Yeah, could you go back a slide?
This one.
Yeah.
This one?
So I guess my question is, like, what's the resolution of your customer data? Like, is this like households, or like what kind of resolution do you guys have with that data?
Oh, every meter. So every meter in our CCMB.
Okay, so it's literally down to each like household or customer's meter then.
Yep.
Cool, thank you.
Mhm.
And I guess going on to the next slide, what is Cascade's like peak day standard? Because in the past it's kind of moved around a bit. Is that?
Oh, I'll cover that. So I think we'd have to go back a slide, but it's that slide. So it's the 30-year historical weather trend. I think that's what you're asking, right? What the average daily temperature, the philosophy on how we get that.
Okay, so you guys are doing a 1 in 30 as your peak day standard.
Yeah, it's the coldest day or the coldest average daily temperature in the last 30 years.
Okay.
So it does slide because every 30 years, your time's changing. And I know we had one fall off. And I know, I think it might have been I think it was 2 years ago, we exceeded the degree day or the peak degree day in Bellingham, which was a bit of a surprise. So.
Just, I guess another kind of follow-up question is the distribution system, like peak day that you guys are designing around, does your methodology line up with the peak day design for like the IRP when it comes to like portfolio design and stuff like that, and like storage and stuff? Are you guys using the same methodology? Does it all align, or is there a separate methodology for system planning?
I'm going to get into how we get to our 5-year growth modeling, but I'll just go through it briefly, and then we don't have to go. We can touch on it later. So
Okay.
Cascade takes our our peak degree day models, so our design day models, and then we apply our growth to those models. And that's how we do our forecasting and things for the IRP. Because I would say your degree day model right now is like our system right now, kind of today. So if you want to go out the 5 years, that we're supposed to assess for the IRP, you got to add some growth if it applies.
Okay. I guess my next question I had for a few slides down, into the future, I think slide 23, I think. How has Cascade's 5-year growth prediction changed since the previous IRP?
I will answer that on the next one.
Okay, great.
I can give a little bit of an update, and Brian's on here, but yeah, Brian does a lot of that growth predictions for us.
Okay.
Mhm.
Thank you.
Yeah, let's hold that, and then we can build to that. That's okay. Okay, any other questions? I know I was actually pausing because this slide normally gets a lot of questions, or we usually have good discussions on it. Okay. We can always come back there. So yeah, so we were just getting to this one. So with our models, we spend a lot of resources on getting our models are really accurate, most accurate data we can have, rebuilding them on, frequently. And then these models really are a great tool for us. So we have lots of capabilities. Every day our engineers use our synergy models. They review large customer requests. We model our RNG. It supports design and sizing of pipe and pipeline components. We use them for future planning. We're just touching on that. We're going to use them to model our IRP predicted growth. We use them to identify the deficits. Operation supports another one on here. System reliability. And then we optimize our distribution system enhancement options with the models. So great tool and resource. And then I'm going to touch on demand side management. So this demand side management, like I said, we've kind of talked about this, but when we get our growth predictions, and this slide, I guess now I'm thinking maybe out of order, but it's okay. So like I said, with our, since we're going to model out our 5-year growth, that growth includes, energy efficiency programs or, if we have some demand side management planned, that would be built into our 5-year predictions. Also, any energy efficiency or demand side management efforts that have been completed, when we rebuild the models, it would be incorporated into the model. So like I said, like that window of that looking back and getting the most recent 5 years of CC&B data, you can get your energy efficiency programs or other efforts, or if they changed equipment or whatever happened to on the customer side for their usage. And then another thing that we could use this for is it could be considered as an alternative to address a deficit. So we could also model demand side management in the synergy models. So. And then I got an update. This one's kind of exciting. So renewable natural gas, it's just a modeling
Kathleen,
update.
we have a question on the last slide.
Oh, yeah, go ahead.
Sorry about that. The way that you described it just now, and I want to make sure I'm not misunderstanding, it sounds like a lot of your growth predictions are based on historical data. Is that accurate?
That would be on Brian. It's like he uses historical, but it's also forward looking in like regulation and different things we see coming. But I hear Brian.
Yeah, so Byron, what I'd be providing to the engineering group is a couple of different growth scenarios. One of those being the building codes with the building stock attrition rate, which would be likely negative growth, some slight negative growth. So in here, the growth predictions would end up being negative. But I'm also going to send over one where the building codes are redacted, and then take a look at if customer counts start to go back up. That way, our distribution system planning side is prepared for that scenario if it happens.
Yeah, that makes sense. Yeah, I appreciate that clarification, Brent. I just wanted to make sure that there's like a consistent methodology being used on distribution system planning versus the IRP like portfolio analysis. Thank you.
Yep.
Yeah, it's kind of the best knowledge you have, of what you think is going to happen in the next 5 years. And it all goes back into the iterative, every 2 years we redo the IRP and, tweak things as needed, can change or push a project further back, etc. So. Okay, so back to my exciting update. Cascade now has RNG flowing into our system. We have 2 sites that just came online in the last couple weeks, the Horn Rapids landfill and the Lamb Weston RNG sites. Both of these are in Richland, Washington. So that's really exciting. And then we're still seeing significant interest from RNG developers in our territory. And then we will have additional RNG projects coming online in 2024. So a couple I know are in construction and are expected for 2024. And then with this, I'm just going to touch kind of from a modeling perspective, because this is distribution system modeling. But we currently model our RNG at 1/100th of the contract demand in our design day models. And I'm going to talk a little bit about our philosophy on this. So typically, and I've done a couple RNG projects in Idaho, and IGC has a couple that have been on now for several years. So we have some like insight in our utility group on performance of the RNG. So typically, in my experience, a new RNG producer, they're kind of unreliable in the beginning. They're still working out like operations issues on their side. They kind of have growing pains. It also can take a little while for their digesters to get all conditioned. So in some RNGs, the first even 2 years, they'll have reduced output. And then once everything kind of gets operating smoothly, they got the bugs working, all their operations like working for their their specific process, they'll get, they'll produce more. So they're kind of unreliable in the beginning, and that's why right now we're modeling them low. They could also be unreliable because to put them in the design day model, we'd have to they'd have to be reliable on that peak day, so that cold day, so when the temperatures are really cold. And we also know that with RNG, due to the anaerobic digestion, some of the bugs are temperature sensitive. So you'll see reduced yields when the temperatures drop, and they'll see swings or just problems they'll fight regulating the temperatures. RNGs can also be shut in if they're not meeting our gas quality specs. So they could, some of the operational issues on their side may cause them not to meet our gas quality specs, and then they'd be shut in and not able to flow on our system. So just with all that, we model them right now low. Like I said, these ones just came on in the last couple weeks. Over time, if a producer gets more reliable, I think on a case-by-case basis, we could, consider them more reliable and maybe increase what we expect from them in a design day. But we're kind of conservative right now, want to see how these guys perform over time, and we want them to have reliable production on those cold days. So yeah, so that kind of covers our modeling process. And now we're going to get into covering how we identify our deficits and constraints. So we'll start with, what is a capacity deficit? It's basically a critical system that has reached a limiting capacity. Some examples of this might include pipeline bottlenecks, minimum pressure to a regulator station, or just another high pressure system or distribution system, not meeting a required customer delivery pressure, or it could also be a physical component limiting capacity. Like, for instance, compressors, they have a specific capacity based on their horsepower curve to be able to get the suction and discharge. They also, another component that has, a stated capacity to be a regulator. And then another example of a deficit is potentially high velocity in a pipeline, which is a good design practice. And so I'll expand a little bit, but the one that I think is the trickiest is understanding the pressure. So I like to kind of talk through an example. So my example might be, I have a 300-pound MAOP pipeline. It runs 5 miles. And at the end of that 300-pound system, I'm going to feed a 60-pound system. So if and basically, we'll keep this kind of simple, but basically as load increases on a pipeline, pressure will drop down the line. So if at the end of the 300-pound system, my pressure is compromised and I can't feed my 60-pound system, I would then compromise my 60-pound system. So that's kind of how the pressures relate. And that would be a deficit. So if my 300-pound system was exhausted down, the end of the line was 40 pounds, that 40 pounds, likely compromises the 60-pound system. So that's kind of just a high level example of what we mean by pressures. We can get in. So this actually is the growth modeling, what I'm just going to cover. So this kind of builds us into our deficits. So I think I mentioned this. I think this might be the one we come back. And there might be a question. We'll see. We'll see where we go. I'll present and then we can see if there's questions. So we model out our 5-year growth predicted, kind of like we were just talking with Brian and our philosophy on that. So we take that 5-year growth that we get from regulatory, and then we add that to our design day models to determine if and when a capacity deficit exists. And then I'll get into this a little bit. So I think this was the question I kind of recalling, but it was if we had, you were asking if we had negative forecast, and then how Cascade's kind of growth predictions have changed over time. In some of our areas and towns, I know I've seen we have had no growth, or the prediction in 5 years is the same as what it is right now. I know one of those, I can name it as well. I think Othello. So the Othello gate was one of them I noticed, or it's kind of becoming more common, and it's kind of happened in the last couple years. It's been kind of surprising to see no growth in certain areas. And for whatever reason, economic, lots of things play into those. But yeah, does that work, Brian? Or yeah, we can continue. Before I move on to the next bullets, we can talk about that too.
I have a question about kind of like degrowth modeling. In previous meetings, Brian had mentioned the idea of converting some lengths of pipe over to like telecoms. Is that accurate, Brian?
That is some of the conversations I've had. I don't know. I don't have any experience with it. But I was talking to folks in the gas supply group about stranded assets and just trying to understand better what that looked like. And I can't speak as to how quick we'd be able to move things to telecom or anything like that, but that was one of the options I heard. Yeah.
Okay. We've also heard some discussions from some think tanks about the ideas of like system pruning and stuff like that in degrowth scenarios in order to minimize fixed costs. Would your synergy analysis be able to evaluate scenarios like that?
I think our engineers would use synergy to do that. It wouldn't be like something that we'd have to check synergy, but you mean like if we do use synergy regularly, like sometimes we'll take things out of service, or if there's a relocate, we do sometimes abandon pipe and things, and we use synergy as a tool there.
Okay. Yeah. I appreciate that. I mean, it's very new to me, so it's always kind of interesting to try and understand what the capabilities are and what you can and can't do with your analysis. So I appreciate that. Thank you.
Yeah, and the pruning is interesting, but typically we do have loops and feeds throughout our system. And normally, a lot of times in the distribution system, it doesn't work as much on high pressure, but you could, take some loops out and still be okay pressure wise, because things just happen over time as your system builds, or maybe you put a new reg on the other side of town, or so yeah, we look at that, or we do that some for operation stuff. I know I've had like projects where they've been like replacing a bridge. That's really popular in some of the infrastructure bills. And then our gas line may be hanging on the bridge, or we might have drilled the bridge, but now we're in the way of like a piling or something, some construction of the bridge. So we've looked at, can we, we kind of ask questions, can we temporarily take it out of service? Or do we replace it in a new area, or can we just eliminate the crossing? In some instances, we can eliminate some of those. So I've seen that in my experience, and that's what Synergy is used for. So engineers do assessments on that.
Yeah, I think the degrowth or like negative growth scenarios are going to be a lot of kind of like unfamiliar territory for a lot of people. So I'm very much looking forward to seeing like the kind of analysis that your team is able to do. So I appreciate your feedback and your insights here. Thank you.
Yeah, and then I'll expand on growth modeling. So when we get our growth modeling, and if there is growth, we're talking about, we typically do it's an iterative process to to add the growth, and then we try to predict the deficit timing. And some systems can, depending on what's happened, maybe there's been more recent reinforcements in a system, or, like I said, maybe there's now regs or different things that have helped the system over time. Some of them can take the growth no problem, but some of them, it turns into a little bit of an intensive process if it can't support the growth, because sometimes if a more significant reinforcement's needed, more time for alternative analysis and just more time to add the growth and get the timing right. So we'll try to predict in the 5 years when we need it. So if it's like 2026, we got a plan and design to get it in time for the deficit. So that's kind of how growth modeling works. And then really the whole goal of it is to make sure we can support all of our growth and just maintain our reliable service during our peak demand events. So, and then with that, once you put the growth models on, kind of like I've been mentioning, we do our system review. So we do comprehensive review every 2 years as part of the IRP. And then we also do yearly reviews with our budget cycle. So typically we're doing reviews on annual basis also. And then if any deficits predicted, we evaluate, we'll propose reinforcements and enhancement options, go through alternative analysis. And then typically we'll work with management to get those into the capital budget based on the timing needs that we've kind of determined with modeling. And next, now that we've kind of covered, the point that gets us to the alternatives, I'll go over our options and kind of our alternative analysis in more detail. So with enhancement, we've kind of talked about this, but some of the options for pipelines, this is just to kind of get everyone talking the lingo to set us up for our next meeting. We have things called reinforcements, replacements, loops and backfeeds. Could be pressure increases or upgrades. Typically, these will gain capacity. We can also upgrade facilities. That might be replacing the whole facility, replacing a part in the facility, things like that. Another option we kind of have is we can always add reg stations to a distribution system. Typically, a reg station is a fresh source of gas. So on distribution, that they typically, will serve 60 pounds. So if you have a system, let's say the east side of towns, has low pressure. If you run a reg over to the east side of town, typically you can boost pressure productively by adding another reg station, having a fresh feed of 60 pounds into the system, or a loop, looping, 2 regs feeding the system too. You can also do like strategically placed gate stations, and then you can also add compressor stations where as feasible. So now I'm going to go through an example. So this is theoretical only, but this is a chart. This is a Synergy modeling example. So this is a distribution system. I see a little high pressure. I see a couple regs, and then pressures by color. So what we're concerned about in this example is the red pipe, which is pressure below 10 pounds. So we'd be looking at how we fix this. And like I said, I'm looking at this high fix. So both the regs I noticed are on the east side of town. So one option, if you brought a reg over to the west, that would probably help it. Or even to the south. Or you could do some looping. So you can go through and this slide's animated. You know, and some things might be unfeasible, like I noted a compressor station. So regs, there's the two regs. What can we do? Here's some pipes. So these are two good piping loops. And you know, I guess with synergy and our engineers, you know, we always things might work in synergy, but one thing we always want to kind of be careful of is that it's constructible. So in this example, that the middle pipe looks really good, but it actually runs through an airport. So it's good, like things can work in synergy, but they also need to work in the real world too. So we typically, you know, as we go through alternative analysis, you know, we typically model out some things and then we'll like look into if they're constructible, practical, and go through our alternative analysis criteria, which we'll be covering in a minute. But a good example here. So you would choose in this example, yeah, this bottom, the lower loop, you know, is constructible. So that would be the option you would choose. And then it's important that, you know, we don't want to overbuild areas. So you'll notice we just brought this back up above 10 pounds. So whatever your kind of your design or your deficit goal is, we kind of want to do the least cost option. So that kind of works through the example, but things, you know, once we have those deficits identified and we have a couple options modeled, we'll go through, you know, how we do alternative analysis, and we'll look at scope, cost, capacity increase, timing, system benefits, maybe long-term planning comes into play. You know, work through alternative analysis and then also environmental impacts. So environmental impacts could be things like, you know, if the pipeline route goes through wetlands or an archaeologically sensitive site, things like that you maybe want to avoid. And then, you know, each enhancement option, I guess, will have different pros and cons. So we kind of weigh them out. And there might be several factors why you select one alternative over another. So now I'm going to cover how we review and select projects to our capital budget. Yeah.
Hey,
go ahead.
Kathleen, we have a question.
Okay.
So Byron here again. Going back one slide.
Okay.
Has Cascade started looking at how to develop any like equity enhancement considerations? So like looking at like demographics of like communities that are impacted, property owners, renters, or like, for example, like equity-based environmental impacts. So for example, like if a particular community might be overly burdened by a compressor or something and they happen to be like a historically marginalized community or something like that. Does that factor into any of your analysis? Have you guys started looking at those sorts of things?
Equity's a tough one. We've had some discussions. But yeah, I haven't had it. Yeah, we probably need more discussions. I know that's come up in some of Naomi's stuff too. So it's been something we've kind of been trying to figure out how to address. I don't know if someone else on here maybe has a little more input they could share, but
I think Noemi's out
oh, okay.
this week, and then Lori is busy on another call.
Okay.
So Byron, we may need to let you know afterwards. We'll follow up on the progress we've made in terms of equity on distribution system planning.
Okay, awesome. Thank you, Brian. Thank you, Kathleen.
Mhm. Yeah, sometimes I guess my thoughts are I've seen it on when you have a low pressure area. You know, the deficit's there regardless of, you know, I guess social economics. So it's kind of tough because, you know, yeah. Okay, so now we'll cover how things get into our capital budget. So like I said, when we go through alternative analysis, we're normally trying to pick like the shortest segment of pipe, lowest cost option, most favorable construction conditions. We want to minimize environmental impact concerns. And we do try to, Byron, this kind of goes into your question on, or comment on equity. We do consider impacts to the community. So like you said, a compressor, I would think, regardless of who the community is, like if we were to put a compressor in, we would have the same separation, whatever's required in our permitting, like, so things like that. But yeah, they would tie into that, or our procedures or things like that, or best practices. Because we do think things like noise and sound into a lot of our design. Basically our sites have been getting bigger, which makes them a little more expensive. And then we'll also sometimes, and this could do with long-term planning, or if there's interest or, other things going on, maybe if we're running down on a new road, or that's in consideration, might allow, customers that are wanting gas to get gas service. So new opportunities could be considered. And then I think I mentioned before, but construction cost. So lots of things kind of build into the alternative analysis that we give thought to, before we select the project. And then this kind of builds into everything we've been talking about. So this slide kind of it's a good visual. So we build in our 5-year IRP growth, build those into the design day models, and then we also take information from our districts and or engineers that just support the districts. So city developments, new housing developments, maybe where a new commercial area is going in, or if the city's developing a new industrial site, all that's kind of incorporated into our process. Like all that knowledge kind of combines, to help us identify system limitations. And another example of, district information, it would be like some roads, or with some of the growth going on in our territory, a road might be going to 5 lanes or something, and it might be a good opportunity for us to get a project, or we might have to move a project, or like I said, some of those bridge projects. So some of that's kind of incorporated too. Maybe you move somewhere else, or maybe you can abandon the feed. But yeah, so once we get all that knowledge in, we got those into our models and kind of into our minds when we're doing our alternative analysis, but we'll identify our system limitations. And then from there, a lot of our engineers work collaboratively with our managers and directors on project selection. So we typically, we'll have our alternatives listed out, and this is what we'll be going through in the July meeting, but we'll share all the alternatives considered, some details on the alternatives, different pros and cons of each one. So we get those projects selected, and then typically we'll rank them. So then we'll prioritize them based on timing, need, and then all that kind of gets built into our capital budget. And a lot of those 2 middle blocks, a lot of it has to do with, benefits, feasibility, cost, all that's kind of discussed and talked about up until we kind of select the project and then place it into the budget. And so a lot of this we're working on right now, actually. So we're working on our growth modeling and alternative analysis right now. And then we'll be sharing that in July, like I mentioned. And then our capital budget, typically we do our first round of budgeting in June. So we'll have our first budget, and then it normally goes through a couple iterations and things, and then it normally gets finalized at the end of November. So in July, we'll have like recommended projects, but it won't quite be our final budget, but it'll be pretty close. But our whole IRP process is kind of iterative. So if things change and as information changes, like you might get new information from the district, or, different things going on, it can change a bit, and we can, adjust our capital budget a little bit as needed. And then, like I said, this is kind of our ongoing steps. So we are working on the 5-year growth modeling. We'll be proposing, evaluating alternatives to address the deficits if we have them. And then we'll be discussing those deficits and alternatives with management. Then we'll be working through our alternative analysis process to select the projects and then get them placed into the budget. And that actually concludes my presentation. So kind of as a wrap up, like I mentioned, this sets us up nice for July. We will be covering the actual projects with alternative analysis and all our considerations. And then the projects were, the alternative we're kind of recommending or selecting at the time. But yeah, I'll open it up if anyone has any comments or ideas or something else. Maybe Cascade should or could consider it regarding distribution system planning.
Kathleen, I
Okay.
have a question.
Okay.
It's Abe Abdallah from Oregon Public Utility Commission. Thank you for an excellent presentation. I just have a couple of questions, high level.
Okay.
One is, do you think that the 5-year process is sufficient for alternatives, as we've seen in the past, whether that's demand side management or any non-pipe alternatives? And do you keep things on the radar for longer than that? So that's the first question. The other question is, do you look at, I mean, you mentioned energy efficiency and possibly you have, from what I've seen in the past, interruptible load, but did you look at curtailing load during peak times, and whether that is, what are the barriers for that, contracting for curtailing, especially for big industrial? So it's not necessarily shutting off the whole gas, but curtailing the gas for maybe non-essential processes, for demand to reduce the demand to be able to ride over the peak. And this is something that probably electrical systems do quite a bit, instead of, as you would appreciate, peak times could be about 8 hours the whole year, and instead of running wires and poles and wires, for that would be cheaper to actually do that kind of alternative. So I'm just wondering if in the gas world you can do that or not. Thank you.
Yeah, I'll go through your questions. I took pretty good notes, but we can, I'll give my answers and then we can follow up, or if I missed something, let me know. But you talked about the 5-year process, and I know we have had discussions with Oregon on going 10 years.
Yes.
I think you got to start at 5 years. So and I maybe could see the longer process. I think what's hard right now is the regulations, like, especially in Washington, we have building codes. It's hard to predict even 5 years right now for us. And Brian and his group, regulatory, knows more on that. But from what I'm hearing, our growth predictions were a little more challenging this year. And I would think 10 years would be even more challenging. So I think just with regulations and, emissions and all those things going on, electrification, what'll happen, with governments, things like that. So I could see that 10 and the reason we discussed 10 with Oregon, or we were considering going 10, is for demand side management. So we had done a pilot, and needed more time. So basically we didn't have enough time we're looking at Baker and Ontario, offsetting distribution reinforcements with DSM, but there just wasn't enough time. So if you modeled out 10 years, that would be how you'd gain the time. But the thing I would kind of question, or I would have a hard time with, is that 10-year growth accurate? Or some of the things we talked about in this, or you're going to be losing customers. I don't know. It's tough.
Yeah, I didn't mean that 10 replaces 5. because you would have obviously things that are happening much faster than even 5. I'm just saying that you might lose opportunities for alternative solutions if it takes longer than 5 to set up and get going, or it's to design it and implement it and all this. So I'm just thinking, would you be losing solutions if you haven't started earlier, that you have to go to a pipe solution because you don't have time? Because that's what we see with gas utilities, that they say, oh well, it's too late now, the growth just happened, and then we get a bit frustrated saying, well, we've mentioned that in 2 IRPs ago and nothing happened, and then suddenly it's become an issue. So just
Yeah, it's a
sharing
good
that.
discussion, but yeah, I think
Yeah.
Cascade would need like a commitment from upper management, because I do think it's quite a bit more time and resources to go to the 10-year.
Yeah.
It's like I said, your models are going to be stretching them to more extremes, and depending on if they can take growth or not, I think I touched, but it can be pretty iterative, and it can be pretty time consuming when you break models with all the growth if it's there in the 10-year.
Just gonna
Thanks.
follow up. Might there be any kind of like path dependency issues without looking like further out into the future? So like, for example, like if there are a lot of like, say, system updates that need to be made in order to bring hydrogen onto the system, could there be path dependency issues and kind of collateral costs associated with that if we aren't planning far enough out into the future?
I don't know. That one's kind of tough to say. I think in general, our understanding is our systems could take hydrogen, but there could be some favorable systems, maybe even newer pipe that could do hydrogen hubs.
Mhm. I mean,
Yeah.
so part of staff's kind of concern here is like projecting out, say, like 10, 15 years into the future. And I understand that like it's really hard because of like the degree of like atomization and resolution that you need for your planning. But staff's kind of concern is that going out into the future, we have here in Washington, we have the CCA, which, assuming that it sticks around, is going to be kind of putting a thumb on the scale and increasing costs on customers. And, there's going to be a certain kind of threshold of where customers start to leave service as a result of price pressures. We don't know exactly where that threshold is. But at the same time, there's this kind of positive feedback loop associated with that around the increasing ratio of fixed cost customers. And so like the ability of Cascade to rein in those fixed costs is a really, really powerful kind of question here about the ability to mitigate these kind of systemic instabilities. And so being able to plan further out into the future means that we'd be able to have these kind of, even if rudimentary, kind of like